Hello and welcome into this first video of the series From Zero to Motoko. This series of videos will provide help and resources on how to start building on the internet computer. Today is the video number 0. Before starting any coding, I want to explain a few of the core concepts of the internet computer. So this is the goal of this video. We are going to talk about nodes, canisters, subnets, data centers. So the internet computer is a very complex network. You don't need to know everything to start building on it, but you do need some basic understanding, I believe. Here's an overview of the network. This is how I see the network. So we can start with the data centers. We have independent data centers around the world, and without them, nothing would be possible, of course. Data centers are here to provide nodes, and actually we can go and look at the dashboard of the internet computer to see data centers. So let's do it. So here we are on the internet computer dashboard. This dashboard was made by a member of the community, Dylan Miller, so thanks to him. We can see a lot of interesting information on the dashboard, and we can see the data centers. So we have data centers in the USA and we have data centers in Europe. We also have a data center in Singapore, and one is coming in Japan. Upcoming node in red. And if we look at one data center, so for example, if I click here, so Portland, we can see that we have 9 nodes inside this data center. So as I said previously, data centers are here to provide nodes, and each data center provides a different number of nodes. And even inside a data center, you can have different node providers. So for example, here in Atlanta, we have one data center, but we have 8 different node providers. So I believe it's the internal organization of the data center. And for this one, we have only one, but we have 9 nodes. And so we have, for the whole network, I don't know if this is the last figures, but I believe so. We have 53 node providers and 174 node machines. So that's pretty cool, but that's going to improve, of course. And we need more data centers in different parts of the world. So to end with data centers and nodes, you need to understand that nodes are what provide computation and storage to the network. Nodes are basically CPU and RAMs, and node providers need to follow some performance requirements to enter the network. So for the moment, if we want to be transparent, the network is not as open as the Bitcoin or the Ethereum network. But this is going to change, and in the future, as the network will grow older and more efficient, more resistant, there are plans to open the network to as much people and infrastructure as possible. And here's a list of the few data centers that are currently working with the internet computer. Okay, so back to our overview. We have explained data centers and nodes. And so after the nodes, there is something really interesting that happened, and that's the real part of the decentralization of the network. This is where decentralization happens. Is that for each for a certain group of nodes, they are going to be regrouped into subnets. And so a subnet is basically just a collection of different nodes from different data centers around the world. And a subnet will have a replication factor. A replication factor of a subnet is the number of nodes that is inside a subnet. So here we can see 5 nodes. Actually, the picture is misrepresenting, is misleading, because the minimum number of nodes inside a subnet is 7. So that's the minimum number, because we can have more, and it depends on the subnet. So that's a really interesting property of the internet computer, and I believe that's why the internet computer is going to succeed over other blockchain technology. This is because you can configure for each subnet how many decentralization you want. So for example, for basic application, you don't need maybe as much decentralization as for critical and maybe even political applications of your services. So we can imagine different subnets with different replication factor. Let's talk about consensus and subnets. This is a very important part because this is where the network is created, basically, and decentralized. What I mean is that without the consensus mechanism, we would just have separated nodes. All those different nodes, so here we have 7 nodes, will reach a consensus through the consensus mechanism, and they will reach an agreement on their current state. So the consensus mechanism is the protocol that allows all those different machines to reach this agreement. And the consensus mechanism is very complex. It involves a lot of cryptography and mathematics, so we are not going to dive into. But we need to know that the consensus mechanism is also where we are going to take care of eventual malicious nodes. So what I mean is that let's imagine that here we are inside those nodes, we are hosting an application. So for example, Uniswap like application. And so this node is hosted by a malicious data center, and this person is trying to change, for example, the amount of currency he has on his portfolio. And so basically he's going to change the state of its node, and that's possible. But what is going to happen is that at a network level, so there will be this consensus mechanism, and the network is going to detect that this node, so the node number 1, is malicious or is not working correctly. So the network will basically say that the majority the other nodes are right, and so this is where the network is decentralized and securized, I would say. So a subnet, as I said, is a combination of multiple replica nodes from different data centers. They work together to replicate the data and the computation that is going on inside the nodes. And each subnet can be thought as its own network, and I would say even its own blockchain-like. And a property that is very interesting is this different replica factors, where we can have different types of application hosted inside. So here we are on ic.rocks. So this is another dashboard for the internet computer. It was also made by a member of the community called Norton Wang. Sorry for the pronunciation. And this is a very interesting website. There are a lot of information here. So congratulations to him for putting this website and all those informations. So actually, talking about subnets, we can see that the current internet computer has 18 subnets, and so I think we can see the different subnets. So as I said, we have nodes inside subnets and canisters. So canisters are more numerous than nodes, of course, and what we can see is that we have all those different nodes for different kind of subnet. So I suppose the system subnet is the subnet that is hosting the NNS. So for those of you who are not familiar, the NNS is basically what controls the network. And so of course this subnet is more decentralized than the other because it's the most critical part of the network. And so 7 is the lowest replica factor, and I believe 13 is for fiduciary subnet. And actually we can look inside the subnet, so maybe this one, and we can see that we have different nodes and different providers. So we have all the providers in green, and we have all the nodes in blue. And so this subnet host is composed of 10 nodes and is hosting 176 canisters. Okay, so we've done data centers, we've understood nodes and subnets. Now is the time to get into canisters. Canisters are what I consider to be the most important aspect of the internet computer for a developer, because the canister is where your code is going to be uploaded, and the canister is what users are going to interact with. They are going to get the front end from the canister, and they are going to interact with the backend. So I put the canister in the middle because we have the developer here. He will upload his code. We have the user. He will use the canister to access services or websites hosted on canister, so hosted on the internet computer, of course. And an important aspect as well is that canister can communicate between them. So we can imagine services on the internet computer communicate through their canisters. Okay, so about canisters. Canisters are the building block of the internet computer at a developer level. And there are multiple canisters per subnet, as we've seen on ic.rocks. We've seen that, for example, on the subnet, we had 178 canisters, I believe. And each canister is going to contain some code and some state. So basically an application or a service. For those of you who come from Ethereum, you can think of canisters as super smart contracts. They can host many data, more data than smart contracts, and they can make as much computation as you want, almost. Every application on the internet computer is composed of canisters, of course, and a basic structure we are going to see is for an application to have one canister for the backend and one canister for the front end. For bigger applications, this is not possible because canisters have limitation in terms of data and in terms of requests per second. But for a simple application, it's the structure that you need to have in mind. At a more technical level, a canister is a WebAssembly module. So WebAssembly is a low-level language, really low-level language that is very powerful, very efficient, and can be used on a lot of different platforms. So this is why it is used for the internet computer. And I encourage you to learn more about WebAssembly because I believe it's the future. So canisters are WebAssembly module with some memory, and you are not going to write your application on WebAssembly, of course. So you need a language that can compile to WebAssembly to create a canister. Currently, on the internet computer, developers are using Rust and Motoko. So Rust is more for advanced developers, and you can do pretty much anything with Rust. A lot of configuration is possible in your canister. Motoko provides more functionality, I would say, but is more targeted for quick integration into the internet computer ecosystem. And it's a very efficient language for basic applications, I would say. Very good structure, and a lot of things have been pre-thought for you. So writing code with Motoko is pretty a pleasant experience. At a more technical level, a canister is just a WebAssembly module. So WebAssembly is a very low-level language, almost machine code, but okay. At a more technical level, a canister is a WebAssembly module. So you have the WebAssembly code and the WebAssembly memory. The memory. And all those WebAssembly modules are okay, so at a more technical level, a canister is just a WebAssembly module. So you have the bytecode and the memory. Basically, WebAssembly is a very low-level language, so it's a very powerful language, very efficient, and very adaptable. So what I mean is that you can use it on really almost any machine that exists. So that's very cool property for a distributed system like the internet computer. And if you want to know more about WebAssembly, it's a very complex topic, but I encourage you because I believe it's the future. And I will put some links in the description. So to write your canister, your code, you are not going to write that with WebAssembly, of course. So you need a language that can compile to WebAssembly. And currently, developers on the internet computer are using two languages, Rust and Motoko. So Rust is more for, I would say, advanced developers. Rust is more low level than Motoko. You can do more things, and you can, I believe, customize more your canisters and what you can do. But Motoko is very efficient, and Motoko is for the people that are coming and want to quickly have a way to create canisters and applications. If you are looking to build something quickly, Motoko is really for you. And it's a very pleasant experience to write code with Motoko because the language has been designed for the internet computer. So there are a lot of things you don't need to take into account. Everything is ready for you. Okay, we are back on ic.rocks, and I wanted to show you some canisters. Here we can see the last updated canisters on the internet computer, so I think it's pretty cool. Each line represents a canister, and there are different informations. Let's check this one. We can have the canister ID here. It's a type canister. It was hosted on this subnet. It was created 1 hour ago, and it was last updated 1 hour ago, so there is only one version for this canister. We also have the hash of the WebAssembly module of this canister. This canister is a special type of canister. It's the asset type of canister. So this is not a different canister from a theoretical perspective. That's the same kind of canisters that I've been talking about, but it's a pre-built canister that exists and allows you to host easily host front-end on the internet computer. And there are different methods associated with this canister. Maybe we can check. And for example, there is this HTTP request method. So basically, this canister was made by the engineers from the foundation to have an easy storage and easy canister that can deal with HTTP to give front-end to users. We also have the controller tree. Actually, what is fun is that other canisters can deploy other canisters. So you can have some hierarchy where a canister was deployed by someone and then the canister deployed other canisters. And that's exactly what is happening here. We have the original controller. So this is this corresponds to an account, a person. And this person deployed Flick, so the Flick canister, and the Flick canister deployed this canister. So Flick is a service on the internet computer that allow people to easily deploy front-end or static websites on the internet computer. And we also have the ledger account associated with the canister, and I will explain in other videos what the ledger account is about and how you deal with the cost of the computation and the storage of your canister. And as I said previously, we have the canister interface where we can see the different methods you can call on the canister. And every time you have the type of the arguments and you have the type of the answer. And you have all those different methods. Before moving on, I wanted to show some canister. I mean the actual website behind the canister. So this one doesn't seem to work, so maybe let's check another one. I don't know, it's completely random. Maybe this one, let's try. Okay, it's working. What is it? Okay, it's a crypto bet prediction canister. Oh, this is pretty cool. Ranking name prediction. Is there a way to predict? No, there is no way to predict actually. I don't understand, but that's really cool. And that website was delivered through this canister. For the last part of the video, I wanted to go through a basic application and try to understand how everything is structured, how the canister system is working. And for that, we will use the basic template application that is provided with the SDK. So when you install the SDK, I will provide the link in the description. You will have you will be able to generate a new project, and the project looks something like this. So it's a website with a logo, and you can enter a name here. And what's going to happen is that once you click the button, you will have to wait for 2 or 3 seconds, and then an answer will be printed, and this answer is coming from the backend. So we will dive into the code and see how this basic application is structured. Okay, so let's dive into a basic application. On the left, you have a schema that represents how user and canister interact. And on the right, this is the actual code that is being used for the application. So let's start with the code. We can see that we have a source folder, and this is the most interesting folder. Inside of the source folder, we have 2 other folders. The first one is the application folder, and it represents the backend canister here, and it's written in Motoko. As we can see, we have the .mo type, which represents the Motoko language. And it's pretty simple. It's just a public function called greet. You send some text, and it gives you back some text, basically a hello message. That's pretty simple for the backend. And then we have the frontend. So the frontend is made of 2 other folders, source folder and assets folder. And we can see that we have everything we need for the frontend. So if you are not familiar with web development, I strongly suggest that you are that you go and read about HTML, CSS, and JavaScript. And basically, we can see that we have everything we need for a functional frontend. So we have the HTML file, the JavaScript, the CSS, and other assets. So we have this image and some text. And so this second folder represents the frontend canister. Okay, so we have the source files, and now we have the configuration file, so the defects.json file. .json is a language that is used for configuration files. If you don't know JSON, that's not a problem. You just need to know that JSON uses a certain pattern. So you have basically each object has a value that is attached to it. And so we have the canisters here. So from here to here. And we have 2 canisters. So the first one is called application, and it corresponds to this folder. And the other one is the application assets, and it corresponds to the other folder, of course. We can see that we have the type of the first canister, and it's of type Motoko, as I said previously, it's Motoko. And the main file is located inside source application /main.mo. So this is this file. And that's basically everything for the backend. And for the front end, we have more things. First, we have this dependency. So dependency means that once the backend is deployed, the frontend will be deployed as well automatically because it's a dependency. And every time you re-upload, the frontend will be re-uploaded as well. And we can see that this canister is frontend, as I said. And we have the entry point. So this is the file that is going to be opened by the user, so index.html. And we have the source folders for the assets, so for the CSS and the pictures. And we have this dist folder, which doesn't exist currently, but once we build our application, the dist folder, will exist, and it will serve as a source folder. And we can see that this canister is of type assets. So about assets canister, they are not different canister. So everything I explained previously about WebAssembly is still true for assets canister, but assets canister are, I would say, pre-built type of canister that is used on the internet computer for front-end development, and they are really useful because you just need to have your front-end files uploaded to the asset canister, and then the user can access those files through HTTP requests. And then we have other configuration about the version of DFX. So I'm using 0.7.2, and about the network. So we can see that I'm not configured for deployment on the internet computer network. I'm just configured for the local development. So I'm using the local address, IP address, and the port 8000. And that's it for the code. So now we can go back to the overview. And we can see that, so we have two canisters, the front end and the back end. The front end is composed of HTML file, CSS file, JavaScript file, and some other assets. And the backend canister is written in Motoko, so the Motoko logo. And once the user will send a HTTP request to the frontend canister, the frontend canister will respond with the frontend files. So I've written that it will send the HTML file to the user, but also the JavaScript and the CSS. And everything will then display on the user side. And the interesting thing is that once the user clicks the Click Me button, the JavaScript code inside the front end of the user will activate, and this JavaScript code will then send a message to the backend canister. The backend canister will treat the message and will answer with the function we've seen, so with the greet function. It will answer with some text. And then the front end of the user will receive the message and will print the message on the web page. So that's it for this application. I hope you understand, and that's it.